Hello everyone. So let's now solve practice assignment week 10 question number 4. Consider two functions defined as follows. If LF1 and LF2 are the linear approximation of F1 and F2 at the point 1, minus 1 and 1, then find the value of 17 times LF1 gradient of LF1 times gradient of LF2. So to calculate the linear approximation for any function, this is the formula. Okay, maybe I should use x dash y dash, x minus x dash, y minus y dash, z minus z dash. So this is the formula for calculating the linear approximation for a function. Now, as we can see here, we need the gradient of f, that is, we need the partial derivative of the function. So let's first start with f1. The given f1 function is ln of x square plus y square plus 2z square. Now to calculate its partial derivative with respect to x. Now, for calculating partial derivative of this function, we can apply the chain rule. That is, we can think one function g of x, y, z as x square plus y square plus 2z square, and h of x, y, z as, let's not, x is ln of x. So this function term here is defined as h of g of x comma y comma z here. So that by chain rule, the derivative of this would become derivative of outside function times the derivative of inside function. That is, first we will differentiate ln of x. So that would become 1 by x. Now here, what is the term that is going inside the outer function, that is g of x comma y comma z, that is this term. So this x here is actually x square plus y square plus 2z square. Now we will multiply it with the derivative of inner function, that is g of x comma y comma z. Now the derivative of this function with respect to x will become 2x, and that's how we are going to differentiate it. So this would become 1 by x square plus y square plus 2z square times 2x. And as we need to calculate it at the point 1 minus 1 1, this would become 2 1 plus 1 plus 2, that is 1 by 2. Now similarly we are going to do for the rest of the partial derivative. This here minus 2 because the y here is negative. This would become minus 1 by 2. For z, for z, 4 upon 1 plus 1 plus 2, and that is 1. Okay, so the gradient of the function f1 at the point 1 minus 1 1, we got it as 1 by 2 minus 1 by 2 and 1. Now if we calculate the function value at the point 1 minus 1 1, so that is ln of x square plus y square plus 2z square, that is ln of 1 plus 1 plus 2, that is ln 4. Okay, now we can put that all these things in the above formula to calculate the linear approximation. So LF1 is given by f1 of at the point 1 minus 1 1 gradient of f1 at 1 minus 1 1 dot with. Now notice that what we are doing is here x dash, y dash and z dash is the point on which we are finding the linear approximation. So we will do x minus x dash, y minus y dash, z minus z dash. So our point on which we are finding linear approximation is 1 comma minus 1 comma 1. So it would be x minus 1. Now y minus minus 1, so it would become y plus 1 and z minus 1. So this we have already calculated. It is ln of 4 plus gradient of f1 at the point is 1 by 2 comma minus 1 by 2 comma 1 dot product with x minus 1 comma y plus 1 comma z plus 1. Simplified ln of 4 plus 1 by 2 times x minus 1 minus 1 by 2 times y plus 1 plus 1 times z plus 1. So here it would be z minus 1. So on simplifying, x by 2 minus half minus y by 2 minus half plus z minus 1. So this minus half would become minus 1, and that minus 1 with this minus 1 would become minus 2. So finally we got ln 4 plus x by 2 minus y by 2 plus z minus 2. So this is the linear approximation for the function f1 at the point 1 comma minus 1 comma 1. But what we need is actually is the gradient of the linear approximation. So if we take the gradient of this LF1, that is now here these are just will become 1 by 2 comma minus 1 by 2 comma 1. Okay. Now what we did above, we will do the same thing for the f2 function also. So given our f2 function is tan inverse x square plus y square plus 2z square. Now first we need to calculate the partial derivative of this function with respect to x, y and z. So just how we applied chain rule for the above function, we will do the same thing here. And at the point 1 comma minus 1 comma 1, this would relate to 2 by 17. So with respect to y, it would become dot 2y, and at the point 1 minus 1 1, this would relate to minus 2 by 17. For z f2 z 4 by 17. And if we calculate the f2 value at the point 1 comma minus 1 comma 1, so that would be tan inverse x square plus y square plus z square, so 2z square. So tan inverse 1 plus 1 plus 2, that is tan inverse 4. Now just put down the above values. So LF2 at x comma y comma z is function value at 1 comma minus 1 comma 1 plus gradient of f2 at 1 comma minus 1 comma 1 dot product with x minus 1, y plus 1, z minus 1. So function value is tan inverse 4. Gradient of f2 is 2 by 17 minus 2 by 17 comma 4 by 17 dot product with x minus 1, y plus 1, z minus 1. Now this is tan inverse 4 2 by 17 x minus 1 minus 2 by 17 y plus 1 plus 4 by 17 z minus 1. Tan inverse 4 2 by 17 x minus 2 by 17 minus 2 by 17 y minus 2 by 17 plus 4z by 17 minus 4 by 17. So adding this quantity, we will get tan inverse 4 plus 2 by 17x minus 2 by 17y plus 4z by 17 minus 8 by 17. Now if we take the gradient of LF2, this would become 2 by 17 minus 2 by 17 and 4 by 17. So that is 17 times. Gradient of LF1 we got this here. 1 by 2 comma minus 1 by 2 comma 1 dot product with 2 by 17 comma minus 2 by 17 comma 4 by 17. This is simplified, we get 17. So okay, here we will get 1 by 17 plus 1 by 17 plus 4 by 17, and that is 17 times 6 by 17, that is 6. So that is our answer. So now if you look at another way to solve this problem, so what we previously did was we need to calculate this quantity. For that, we first calculated the partial derivative of both these functions. Then we tried finding the linear approximation of this function at the point 1 minus 1, 1. Then we find the gradient of that linear approximation function. And then we did the dot product of these two quantity, and 17 times that we got the result. So this was quite a tedious work. So now we are going to look at a shorter approach for the same question. So what we actually need here is the gradient of the linear approximation. So we know that if we want to find the linear approximation for any function, let's say we have some function f, and we want to find the linear approximation of this function at the point x dash comma y dash comma z dash, then this linear approximation is given by function value at that point, that is x dash comma y dash plus z dash, plus gradient of the function at that point dot product with x minus x dash comma y minus y dash comma z minus z dash. So this was how we find the linear approximation. Now, if you want to find the gradient of this linear approximation, then this quantity here would be some constant because we are finding the function value. So this would be constant. So when finding the gradient, that is the partial derivative, this would not play any role. So it would set to 0. Now, let's say the gradient of the function f at the point x dash comma y dash comma z dash is some a comma b comma c. Then what this quantity will result is a comma b comma c dot product with x minus x dash, y minus y dash, z minus z dash. Okay. Now here notice x dash, y dash and z dash is one point while our variables are x, y and z. So this would be our like linear approximation for the function, and on simplifying it, it would be basically a times x minus x dash plus b times y minus y dash plus c times z minus z dash, and that is ax minus ax dash plus by minus by dash plus cz minus cz dash, and that is ax plus by plus cz minus ax dash plus by dash plus cz dash. Notice this would be some constant values. not the variable. Our variables would be here, ax, by, c. Now, if we are going to calculate the gradient of the function now, this should result in a comma b comma c because it is just a simple linear function. And notice that this is actually the gradient of the function at that point. That means if we have any function and we want to find the linear gradient of the linear approximation of the function at some point, then that would be same as the gradient of the function at that point. So we are going to use that thing, that is, instead of finding first linear approximation then gradient of that linear approximation at that point, we will use our result that we just got and take this gradient of the function at the point 1 comma minus 1 comma 1 because you are finding the linear approximation at this point for both the function, and that would be same as the gradient of the linear approximation for those functions. And we will just take the dot product of these two. Whatever result that we will get, we will multiply with that 17 and we will get the same answer. So if we take the dot product of these two quantities, this would result in 1 by 17 plus 1 by 17 plus 4 by 17, and that is 6 by 17. And if we multiply it with 17, then we will get 6 as our answer. So we got the same answer as before. Thank you.